Hi, calculus students. These notes are on areas in the plane. So this is an application of integrals, and it shows us how we can kind of build on our understanding of integrals to find a different type of area. So first we're going to start back with what was our initial understanding of integrals, and specifically definite integrals. So back when we were first exploring definite integrals, we thought about rectangles. So the idea was like if we kind of sum up all these little rectangles between, say, point A and point B along the x-axis, that should tell us approximately the total amount of area between this function f of x and the x-axis. So I'm just going to kind of record what I just said. So we said we think about definite integrals as the sum of all rectangles between, between x equals a and x equals b. So I only drew one of them here, but you can kind of imagine there's a whole bunch of them, and at first we get an approximation, but the way we get the exact value would be to make the rectangles get skinnier and skinnier and skinnier, make there be more and more and more, all the way to infinity number of rectangles. And so the idea of what's the area of just one rectangle, so we could say that the area of one rectangle would be, in this case, the height, the length times the width, or the height times the width. So the height of this one rectangle is exactly the function value at this point C. So we're saying C because we're assuming there's like some x value right here that we're calling C. So you'd say that it would be f of C times the width of the rectangle, which we're calling delta x. I'm just going to label that. So f of C represents the height of the rectangle, and then delta x represents the width of one rectangle. And we want the sum of all these rectangles, and we would like the number as the number of rectangles goes toward infinity. And that's how we get the exact definite integral. So the exact definite integral would be the integral from a to b of f of x dx. And there's a relationship between this notation and our original rectangle formula. So if we think about it, the f of x here is still representing the same thing that f of c represented in this specific rectangle. So this is still the height. And this dx stands for delta x. Dx, right? This is delta x, so is this. So this dx represents that tiny, tiny change in x, and as the number of rectangles goes towards infinity, this value is getting infinitely small. Okay, so this would be our width. And I'm saying this because we're going to start thinking about how can we come up with a slightly different integral to represent something slightly different. So this was our general kind of understanding of integrals in terms of area of rectangles from the beginning of our unit. And now we're going to take a look at what can we do with this. So we're still trying to find the area, but instead of it being the area between a function and the x-axis, now it's the area between two different curves, f and g. So the idea is we can kind of think about this similarly. We can draw a similar rectangle. Between the two curves. So if I draw on that rectangle, I'm just going to kind of pick one x value to think about and then kind of cap it off at the y value of each function. So there is a rectangle, and now the idea would be like, well, we need the area of all such rectangles, and we sum them up in order to get the total area. So the area of the shaded region, we'll say, is the sum of all such rectangles between x equals a and x equals b. Oh, I can't quite read that. Now the question, and as that sum goes to infinity, and I'm going to leave a gap and we'll say as the number of rectangles goes to infinity. So now the question is, how can I define the area of one of these rectangles? Well, first of all, I could say, let's suppose that I chose some x value we're going to call c again, in which case that the height at this point right here would be, this is on the curve g, so this would be g of c, and then up here would be f of c. And we can also still think about kind of the width of the rectangle as being delta x. So in that case, the area of a rectangle should be its height times its width. Well, its width is easy. Its width is still delta x. But how can I determine the height? Well, I know f of c would be the distance from the top function to the x-axis, and g of c is the distance from the bottom function to the x-axis. So if I want just the distance between, I should subtract f of c minus g of c, and that'll give me exactly that height. So that's what I'm going to write. So we have f of c minus g of c, and we're taking that quantity and multiplying it by delta x. And the idea here, my lights just turned off. Hold on. The idea here would be that this whole f of c minus g of c is exactly the height of a rectangle, and the delta x is again the width. So this can translate then into an integral, right? If we think about how did this translate into an integral, we're just integrating the height from a to b. So it's the same idea here. We're going to integrate the height, but now the height is the difference between these two functions. So if we come down to the box along the bottom of the page, it says if f and g are continuous on the interval ab, and g of x is less than or equal to f of x. This is an important idea. So we're always thinking about which function is smaller than the other one, or has smaller y values. Okay, for all x on the interval, then the area of the region bounded by the graphs of f and g and the vertical lines x equals a and x equals b, so those are those two lines there and there, would be the integral from a to b of f of x minus g of x dx, where f of x we're thinking about as being like the top function, and g of x is the bottom function. Okay, so now we're going to flip it over our worksheet and take a look at some examples along the back. Okay, so the first example says we want the area of the region bounded by the graph of y equals x squared plus 2, y equals negative x equals 0, and x equals 1. So first of all, I already gave you the graph, but we're going to try to visualize where exactly is this area. I'm going to use a highlighter to shade in that area, so if you don't have a highlighter, you might want to grab one. So the top function here is y equals x squared plus 2. Then we have the bottom function here is y equals negative x. Now the lines x equals 0 and y equals 0 are vertical lines, right? So that's like the x equals 0 would be along the y-axis, then x equals 1 is the vertical line through the x value of 1. So essentially I'm going to shade the region we're thinking about. So it'd be that whole region. And now you may already be able to tell what integral we're going to set up, and we're just going to focus on the setup of the integral, not actually evaluating it. But I think it's really helpful sometimes to actually draw in the rectangle so you can kind of visualize what you need to do to get the height of that rectangle. So if we draw in a sample rectangle, well, I can see that the top function would be y equals x squared plus 2, and the bottom function is y equals negative x. So, and I want to sum all such rectangles between x equals 0 and x equals 1. So those are basically telling me my a and my b for my limits of integration. So now the integral I would set up then would be the integral from 0 to 1 of x squared plus 2 minus negative x. And you kind of have to be careful with your signs here. And you can kind of put that all in brackets and then write your dx. Now I could just plug this directly into my calculator. In this case I'm actually going to simplify it a little bit, so I would get from 0 to 1, since it's minus a negative, that's really plus, and if I rearrange my terms from highest exponent to lowest exponent, now I have x squared plus x plus 2 dx. Then at that point you could go ahead and put it into your TI and evaluate the integral. This is one you could easily take the antiderivative of, but our focus for this unit is going to be, can we set up the integrals, less so than can we actually take the antiderivative and evaluate. So if you plug this into your calculator, you should get 2.83 repeating, and that represents the area of this integral. If you look at it just in terms of like counting squares, it makes sense because there's 2 full squares and then you have like these 2 other chunks which look like they're almost another square, so that's that 0.83. Okay, so let's look at another example. So in the next example, it says find the area of the region bounded by the graphs of 2 minus x squared and x, or g of x is equals to x. So first of all, let's figure out which one is which in this graph. And if I didn't give you this graph already, you could do this by just going onto your graphing calculator and graphing it. So this would be 2 minus x squared. This would be g of x equals x. And then I want the region bounded by them. So sometimes what happens is it actually creates a closed shape. So then we are assuming that the endpoints would be the points of intersection. And again, if I didn't give you a graph already, you could find those points of intersection on your calculator, or you could find them algebraically by setting the 2 equations equal to each other. So that's the area we're thinking about. I can draw in a sample rectangle. And that just helps me visualize what minus what do I actually need to do when I set up my integral. So now I can see that the top function is actually 2 minus x squared and the bottom function is y equals x. So I'm going to do the integral of 2 minus x squared minus x. And for my limits of integration, I need to go from this point to that point. So I'm taking the sum of all the rectangles in between. So at this point I can see on my graph is -2, and this x value here occurs at 1. So I'm doing the integral from -2 to 1 of 2 minus x squared minus x. I could rearrange this. There's not really any simplifying that needs to happen, but I could just rewrite it as from least to greatest exponent would be -x squared minus x plus 2. And that's what I'm taking the antiderivative of and plugging in those points, or I could just go straight to the calculator at this point, and when I do that I get the value of 4.5. Okay, so we have one more problem to look at, and there's actually 2 ways to solve it. So we're at least going to do way 1 right now. I think I'm going to save way 2 for in class. So the first way we can solve it, so first of all, let's think about where is this region. So it's bounded by the graphs of the square root of x, y equals x minus 2, and the x-axis. So the square root of x is the curve. X minus 2 would be the straight line here, and the x-axis. So if I'm going to shade that region, it's that. Now this one problem is a little bit different because there's actually, if I choose to draw my sample rectangle, say somewhere after 2, is slightly different than if I choose to draw my sample rectangle somewhere before 2. So the difference is that before 2, I'm going to kind of put like a separation. Before 2, the height of my rectangle is just determined by the square root of x. It's the difference between the square root of x and the x-axis. But after 2, that's where x minus 2 comes into play, and now what determines that height is the square root of x minus 2. So one way of doing this, since the heights are different, there's a different equation for the height in the two different chunks, is I can set up two different integrals, and that's what we're going to do here. So way 1 is set up two integrals. So the first integral would be just before the dashed line, so from 0 to 2. And that is because like our normal understanding of an integral of a function is the distance between that function and the x-axis, this would just be the integral of the square root of x dx. Okay, now I want to add to that the integral, so now to get the rest of the area from 2 to 4, I need to subtract the square root of x minus 2. Okay, and so now I could simplify this a bit, but I can also just plug both of these into my calculator. If I simplified it, this would become the square root of x minus x plus 2. That just allows me to use fewer parentheses when I go to plug in. This one is going to stay exactly the same. And when I plug this into my calculator, and you should check, I get 3.3 repeating. Okay, so that's all I'm going to cover in this video. There are not any U-try problems today, and we're going to talk about a different way of calculating that same area in class.